All right, so let's get started on a very long problem. We have a 12-ton vapor compression refrigeration system, meaning Q dot N to the evaporator is 12 tons. So this is the evaporator right here. And we can immediately convert that to kilowatts. 211 kilojoules per minute is a ton. So let's put ton per 60 seconds. And we can convert that over, and that comes in at 42.2 kilowatts. Okay, so that's our cooling. Refrigerant 134A is the working fluid. The compression process is internally reversible and can be modeled as PV to the 1.01 is equal to a constant. That is a V. That doesn't look like a V, but it is a V. Maybe I put a V and get rid of that looking like a U there. The condenser is water cooled, so we see the condenser right here, and it's cooled by water, so we have cooling water. Comes in at 20 and leaves at 30 degrees C. There's negligible change in the pressure of the water. Good. The heat transfer from the outside of the condenser can be neglected, so no stray heat transfer with the surroundings, just inside the condenser between the refrigerant going through and the cooling water going through. Determine the mass flow rate of the refrigerant in kilograms per second. Well, to do that, we do a control volume around the evaporator, and we do an energy balance. So what do we have? We have the Q dot coming in is equal to the mass flow rate of the refrigerant times the enthalpy leaving minus the enthalpy coming in. Okay, so our mass flow rate of the refrigerant is Q dot N divided by H1 minus H4. So we have 42.2 kilojoules per second. That's kilowatts. Our H1 right down here, 255.27 minus our H4, 112.22 units of kilojoules per kilogram. And we jump on our calculator, we find the mass flow rate of the refrigerant, 0.2950 kilograms per second. And that's our answer to part A. Okay, so there it is for part A. Let's move on to part B. What is the power input and the heat transfer rate for the compressor? So we have this positive W dot going in, and that's important that it's shown going into the compressor. We have this Q dot C going into the compressor. So let's write our first law. So we have, I'm just going to stay with Q dot C going in, W dot C and Q dot C going in, both in, equal to the mass flow rate of the refrigerant, which we just calculated from part A. And we have, it picks up enthalpy H2 minus the H1. So we look, we have our H1, our H2, kind of check. We just calculate our mass flow rate. We have two unknowns in one equation. We're a little stuck. So what we have to do is we have to find another equation. And then we reread the problem statement again and again, and we find, oh, we have a polytropic process. This PV to the 1.01 is equal to a constant, and it's also described as being internally reversible. So we go back to section 6.13.3 in our textbook, which is dealing with work in a polytropic process, and we find that the W dot per M dot for int rev is equal to minus. Notice that that minus sign is for a control volume with the power going out. Okay, so we're going to have to deal with that minus sign. The exponent n divided by n minus 1 times our P2V2 minus P1V1. That's after the integration. So for this problem, our n is equal to 1.01, and our P2 and V2. Here's our pressure at 2. Here's our specific volume at 2 are given. And there's our P1 and V1 are given. And you use the unit conversion that 1 kilopascal times a meter cubed is precisely 1 kilojoule. And we've done this a few times. I'm going to say that I'm going to compute this right here using these pieces of information in the N 1.04, 1.01. And we find that it gives us a negative 43.63 kilojoules of work per kilogram of refrigerant flowing through the compressor. So now we interpret that to get that W dot C is minus this minus of 43.63 for this problem, because in this problem it's shown to be positive inward directed, okay? And we multiply by our mass flow rate, 0.295 kilograms per second, and we calculate that our power into the compressor is a positive 12.872 kilowatts. Okay, you round off to 12.9 kilowatts. Then you can come up here and finish the problem to calculate the rate of heat transfer into the compressor, mass flow rate of the refrigerant, that's H2 minus H1 minus W dot C. So let's substitute our numbers. 0.295 kilograms per second for the mass flow rate. H2, 280.29 minus H1, 255.27. And then we have a minus 12.872 kilowatts. And that generates to a negative 5.49 kilowatts. Now, what does that mean when it's a negative sign? That means that it's actually not into the refrigerant, but it's actually out of the refrigerant to the surroundings. That's what it means. Now, I know that the answer is given just the magnitude of 5.49. We look at the wording on the problem statement. It says the power input and the heat transfer rate for the compressor. So the power is input to the compressor, so that's emphasizing the sign, and I would report that as a positive value. But it really doesn't say, the direction is not really implied in the wording for the heat transfer. The heat transfer rate for the compressor, well, is it the heat transfer rate into the compressor or from the compressor? Because if it's into the compressor, I would put a negative sign in front of that value. If it said from the compressor, I would leave it as a positive. But in this point, what we have to say is that Q dot C for the illustration as shown in the textbook is really opposite of the direction shown. It's from the compressor to the surroundings. I should have probably put a negative sign on the answer right there. Okay, anyway, we know which direction it is. It's from the compressor to the surroundings. Let's go to part C. What is the coefficient of performance? So we have the coefficient of performance for this refrigeration. It's the rate of cooling divided by the rate that the power is supplied. The rate of cooling was calculated to be 12 tons or 2.2 kilowatts divided by the power input, 12.9 kilowatts. The COP refrigeration comes in at the 3.28. All right, that was probably the easiest part C. Let's continue to part D. Okay, what is that? Mass flow rate of the cooling water. Well, let's do a control volume around the condenser, and you have the mass flow rate of the refrigerant. It comes in at high enthalpy, goes out at lower enthalpy. So that's like Q dot out. you might want to even put this as Q dot out of the refrigerant. That's equal to Q dot into the cooling water. Into the cooling water is the mass flow rate of the cooling water times the enthalpy at 6 minus the enthalpy at 5. Apologize for the long run on. This is really not good mathematics, a one line with 3 equal signs, but a lot of people in engineering do it. We understand what's going on. This really in the between is just to help us give names to it. It's like what's out of the refrigerant, it gets into the cooling water. So only unknown in this equation is the mass flow rate of the cooling water. So the mass flow rate of the cooling water is the mass flow rate of the refrigerant times H2 minus H3 divided by H6 minus H5. And luckily they gave us the H5 and 6 right here, as well as all the refrigerant enthalpies. So you calculate the mass flow rate to be 1.19 for the cooling water flow rate. All right, so let's continue on. Okay, what is the rate of entropy production in the condenser, and then do it for the expansion valve? Well, the same control volume for the condenser. And so our rate of entropy production in the condenser is equal to the mass flow rate of the refrigerant times the entropy leaving at 3 minus entropy inlet at 2 plus the mass flow rate of the cooling water times the entropy leaving at 6 minus the entropy in at 5. Now, you may take a few steps to get this, but it's the second law for this control volume. There's no stray heat transfer with the surroundings, so no Q dot divided by TB. And there you go. So we have the S2 and 3 and 6 and 5 and the mass flow rates calculated. And this is the rate of entropy production in that condenser in kilowatts per Kelvin. All right, how about for the expansion valve? The rate of entropy production in the expansion valve is determined by a control volume around that expansion valve, which is just mass flow rate of refrigerant times the exit S4 and the inlet S3. You're given both of the S's right over here in the column of entropies, and this is the rate of entropy production in the expansion valve. Let's continue. Okay, once we calculated the rate of entropy production, we calculate the rate of exergy destruction. Well, if the earlier part is sigma dot, and then you're asked to calculate the rate of exergy destruction, multiply by the dead state temperature, which is given right here to be 20 degrees C. So dead state is 293 Kelvin. And then you'll get the rate of exergy destruction in each of those components. So just take this value for the condenser, multiply by 293 Kelvin. It'll make it into kilowatts. Likewise, here, times 293 Kelvin, and that'll give you the rate of exergy destruction in each of those components. The only thing was they wanted it as a percentage of the compressor input power. Well, so you take that sigma dot times T naught, you divide by W dot into the compressor. And we already found that the compressor input power was 12.9. Okay, so when you do that, you find that around 26% is the percent of exergy destruction in the condenser, and around 8% is the exergy destruction in the expansion valve. Not as much as you might expect. In the expansion valve, you think, oh, that's very wasteful. But hey, if it's less than 10%, look for the other 90% before you focus on improving the expansion valve. All right, let's continue. So this is a little extra G, and this should be H. Okay, calculate the rate of entropy production in extended control volumes around the condenser, extended control volume around the compressor, extended control volume around the evaporator. What do we mean by that? Well, we know that this water goes out and there's another heat exchanger, and it's like the water's going in a loop here. And eventually that heat is transferred. This Q dot that came out of the refrigerant that went into the cooling water is eventually transferred at a TB, that is T naught, your extended control volume, such that the boundary temperature for the heat transfer out of the system is the dead state temperature. That's what we mean. So you do a control volume that doesn't cut the cooling water loop right there. No. It goes way out here and cuts where the heat transfer from the cooling water is to the surroundings. Okay, so if we do that, then what we find is that the sigma dot inside of this extended condenser control volume is equal to the mass flow rate times the that's fine, the S3 minus the S2, just like what we had before. This is that refrigerant. And then we say, well, what is that rate of transfer coming here? Well, it's leaving, so it's going to be minus the Q dot coming out of the refrigerant divided by the TB, which is T naught, 293 Kelvin. All right. So so we can put in some numbers here. The mass flow rate of the refrigerant, that was the let me put it down here, 0.295 kilograms per second. Our S3, 0.4054 minus our S2, 0.9309 kilowatts per Kelvin, plus, this has to be a plus right here, plus the rate of heat transfer from the fluid leaving the refrigerant leaving the condenser, which was 49.581 kilowatts divided by 293 Kelvin. So this comes in at 0.01420 kilowatts per Kelvin. All right, so that's our extended for the condenser. That's a bingo right there. How about the extended for the compressor? Well, okay, either way, we've got to deal with this Q dot C. We know it's negative. I'm going to do this. You're going to hate me for it, but I'm going to turn it around. That way I have fewer minus signs. And then this was the let me go back and look at my numbers here. 5.49. So this is the 5.49 kilowatts, and it's going out of the control volume. I'm going to do an extended control volume around that condenser such that the boundary temperature is the dead state temperature, which is 293. That's what we mean. So this W dot coming into the compressor is still 12.872 kilowatts. Okay. All right, let's write our second law, sigma dot, for the compressor. All right, so we have the mass flow rate of the refrigerant times S2 minus S1 plus, what is that, Q dot leaving the compressor divided by the temperature, the boundary of the compressor. Okay, I'm running out of room. So the mass flow rate of the refrigerant, we did that, 0.295. The S2 is right here. The S1 is right here. S2 and S1. Q dot C, 5.49 kilowatt divided by 293. And you calculate that this is, I shouldn't change color too often, but 0.02051 kilowatts per Kelvin. Bingo. Okay. Now another one, a hard one, which is this evaporator. We want to do it for an extended control volume around the evaporator. If it was a tight control volume, I would have to struggle with what is TB right in here. And that TB, if it's tight, if it's not an extended control volume, would be around the saturation temperature, Tsat, at the pressure of the evaporator, which is about 4 bar. Well, it is 4 bar, but and this would be around 8.93 degrees C. But we want an extended control volume. Okay, so we extend it way back here. And then you have to think and analyze and say, well, this 12 kilotons, what's it doing? Well, it's leaking into our refrigerator. And we're trying to maintain this refrigerator to be cold. So what temperature does it leak into the cold? Well, it leaks in at a boundary temperature, the dead state temperature of 293 Kelvin. Kind of like all of these extended control volumes go out to the dead state temperature. That's for our boundary temperature for entropy calcs. Because once it leaks in, there's a whole lot of exergy destruction pulling it through and into the evaporator. Okay, so sigma dot for the extended evaporator is going to be that mass flow rate of the refrigerant times S1 minus S4. Now we have to pay particular attention. These were both out. This one's out. Okay, and then I had a plus sign in front of the Q dot, but this isn't Q dot N, so it's a minus Q dot N divided by TB. All right, let me just run the numbers here. 0.295 times S1, 0.9249 minus 0.93, whoops, not that, S4. S4 is right here. 0.4179 minus the Q dot coming in 42.2 divided by 293, and we calculate 0.00554. 0.00554, close enough. All right, so that's our rate of entropy production in the extended evaporator. Well, if you go to part H, what is the rate of exergy destruction in the extended condenser, extended compressor, extended evaporator? Well, you just multiply those by our dead state temperatures. So I'm going to just put exergy destruction rate in our condenser, and that's the 293 times that, and you find that it comes in at in the extended condenser 4.16. Exergy destruction rate in our extended compressor comes in at 6.01, and our exergy destruction rate in our extended evaporator comes in at 1.63. All these are kilowatt, and the exergy destruction rate from the previous page for the expansion valve was the 1.08 kilowatts. Okay, so if I add these four up, and I need to scoot down just a little bit, we have the 4.16 in the extended condenser, the 6.01 in the extended compressor, in the expansion valve 1.08 and 1.63, and we get the sum to be 12.88 kilowatts. Well, what came in to our compressor, our W dot into the, let me not scroll down so far. Let me just write it up here. Well, W dot into our compressor was 12.88. I know I rounded off a little bit, but they're the same value, the sum of these. So you can go and do the percentage for what is the rate of exergy destruction in that extended condenser, and that comes in at 32%. Where the previously it wasn't extended, it was just a tight, it was only 26%, but now it's 32%. And then for the compressor, it's 47%. And for the expansion, not expansion valve, evaporator, it comes in at 13%. And for the expansion valve, it was previously a different number, but it's still, well, no, it's still 8.4%. It didn't need an expansion or anything. So when you add these percentages up, you get to 100%. So there's a full Exergy accounting of this system. But I think the cleanest way to think about it is to go ahead and extend the control volume around that evaporator, extend the control volume around the condenser, and then also extend the control volume around, what did I say, condenser? Compressor, and then extend it around the condenser. All right, well, hopefully that was helpful. Thank you.